Antiderivatives. So that means what you think it means. It means doing a derivative backwards. So that's mathematics, right? Every time you learn to do something and then you finally get comfortable with it, we make you do it backwards. It's just like multiplication and division. Now we got to do it backwards. So here's a definition. We're going to use the notation big F, capital F. A function big F of x is an antiderivative of lowercase f of x if f prime of x equals f of x. So something is an antiderivative of a function if its derivative is your original function. So now I'm going to give you a function little f, and you have to give me a function whose derivative is that. It's not as hard as it sounds, and just like with differentiation, there are rules. So let's figure some stuff out. Find an antiderivative for x squared. So you now have to tell me a function whose derivative is x squared. And let's just think about it. We know how to do this. So for something's derivative to be something x squared, the power of that something would have to be 3, right? Because the derivative of something x cubed is something x squared, because by the power rule, when you differentiate, the power goes down. So when we go the other way, the power has to go up. So the power would have to go up to 3. So think about if it was just x cubed. The derivative of x cubed is 3x squared, right? It's not x squared. So you just have to think about how do you cancel out a multiple of 3? Well, you cancel out a multiple of 3 by dividing by 3. So if you had x cubed over 3, right, by the power rule, that would be 3x squared over 3, which would just be x squared. All right, so in general, that's what happens. The power goes up, and then that constant that comes out is a byproduct of the regular power rule, so we then have to divide by that constant. So just convince yourself that, yeah, the derivative of that thing is x squared. So an antiderivative of x squared is x cubed over 3. And then think about, we'll see in general, but think about if it were x cubed or x to the 4th. If it was x to the 4th, okay, it would have to be something x to the 5th. So what would it have to be? X to the 5th over 5, because the derivative of that would be 5x to the 4th over 5, which is x to the 4th. So right off the bat, right, we have a reverse power rule that just works, and it just works backwards. One thing you might have noticed about the verbiage is I'm saying an antiderivative as opposed to the antiderivative. So with regular functions differentiating, we always said the derivative, right? The derivative of sine is cosine. We didn't say a derivative because there's only one. So here's why that language. If I had x cubed over 3 plus 1, or x cubed over 3 minus 100, or x cubed over 3 plus 4 pi, whatever, all of those functions would have the same derivative because the constant just goes away. So you do have this ambiguity where there's not just one right answer. Now there's one simplest answer, and the simplest answer is x cubed over 3. But if I asked you for an antiderivative and you said x cubed over 3 plus 10, you would not be wrong. So that's why we say and not the. And in general, that's it. You always have this ambiguity where you don't know if there's a plus or minus some constant on the end of your antiderivative. Think back to when I gave you the graph of a f prime and I asked you to kind of visualize stuff about f. When we drew f, we didn't know vertically where exactly f was because we can't know. And this is the same rule. If you move a function up or down, it doesn't change the derivative. And so you'll see this plus c. So this is just kind of going to be just good etiquette, where just give me a plus c on the end of any antiderivative you do. So in general, the general antiderivative of f of x is you take your simple antiderivative, big F, and then you just say plus c where c is any constant. You don't even have to say where c is any constant, just say plus c. And c can be negative, so you don't have to say plus or minus c. So that c has a name, we'll talk about it later. We'll see an example at the end of this where you actually can figure out what C is. That's called an initial condition problem. So sometimes C is a specific thing, but for now, where we're just doing backwards differentiation, we're just going to put it in. So same thing, right? you've already kind of thought about this. It had to be something x to the fourth, but if it were just x to the fourth, that 4 would fly out, so we got to divide by a 4. Same exact logic. If you have x to the fourth over 4 plus or minus any constant, then the derivative of that function, any of that family of functions, is going to be just good old x cubed. So that's it. That's what we're going to call the reverse power rule. So if you have x to the n, the power goes up by 1, and then you divide by that same number, right? So if it was x to the 99th, that would be x to the 100th over 100 plus c. This works actually with fractional exponents. This works with negative exponents. We'll see examples of that. Look at that thing, though, that x to the n plus 1 over n plus 1. What's the one number n can't be, right? We have a little problem because we're dividing by something. So if we're dividing by n plus 1, right, n cannot be negative 1. Because then you have x to the 0 over 0, and that's 1 over 0, and that's undefined. So we have a little problem. Whereas the power rule worked for any power no matter what. There's one number that the reverse power rule doesn't work for. However, this is one of those cool places where math just kind of steps in and fills in the gap. Because think about if n were negative 1. That's x to the negative 1. This rule doesn't work. But x to the negative 1 is 1 over x. Right? And we actually do have a function whose derivative is 1 over x. It just so happens it's a completely different kind of function from out of left field. It just kind of swoops in. Right? You're all thinking it. The derivative of natural log of x is 1 over x. So there you go. We have an antiderivative already for x to the negative 1. So now we can do any power. X to any power, if the power isn't negative 1, we just use the reverse power rule. If the power is negative 1, hey, lo and behold, we can just use the natural log. Right? That works. The derivative of natural log of x plus c is always going to just be 1 over x. We're going to make that a little better because of 1 over x. X can be negative, and ln it can't, but we have an easy fix for that we'll look at in a second. Let's do one with a fractional exponent. Sorry, I'm at the bottom of the screen here. For square root of x, so that's the same as x to the 1/2. It's the same rule. It just looks a little different. So the power goes up by 1. 1/2 plus 1 is 3/2. And then you divide by 3/2. So that's a compound fraction. So that's x to the 3/2 over 3/2, which is the same as dividing by a fraction is multiplying by the reciprocal. So that's 2/3 x to the 3/2. So you'll get used to doing that where you can almost skip that step. Say, okay, instead of dividing by that 3/2, you just multiply by the reciprocal. If you left it like over 3/2, well, why not just write that as 2/3? Right, and then just convince yourself that if I gave you 2/3 x to the 3/2, the derivative of that, okay, the 3/2 comes out and cancels out that 2/3, and then that 3/2 drops down to 1/2, and then it's just the square root of x. So you do not have to put it back into radical notation. I did just so you can see, oh, that's a function whose derivative is just the square root of x. You can leave it as 2/3 x to the 3/2. There's really no reason not to. Trig stuff. If I ask you for a function whose derivative is cosine, you know that's sine. So it's sine of x plus or minus whatever. In most cases, see what I mean? This is pretty easy. You're just thinking about, okay, what function has this property? We have to think a little bit here for if we want an antiderivative for sine of x. Well, it's not cosine because the derivative of cosine is negative sine. So if you want a function whose derivative is just sine, if you had negative cosine, the derivative of negative cosine is negative negative sine. So the antiderivative of sine is negative cosine. Don't worry about memorizing these. In the course of this, you'll have the basic rules memorized just automatically. And if you don't have to take Calc 2, you don't have to get too hardcore into this process. We're going to do it. We're going to get to techniques for doing this at the end of this course. But Calc 2 is like all about this, and it's a lot harder than doing derivatives. Sorry. Let's just fill in what we know. let's just kind of make a log of what we know so far and figure out some other basic rules. Again, we're not going to get into the techniques of doing this. There are plenty of techniques, but with going backwards like this, we use the word techniques instead of rules because it doesn't always work. It's hard. So for differentiation, any function I throw at you at this point, you can tell me the derivative of it because there are rules. But if I give you a function, you can't always tell me an antiderivative. And so we talk about techniques of doing it, where it gets more and more complex as Calc 2 wears on. There's our reverse power rule. It works for any exponent, negative, positive, fractional, whatever, except n equals -1. If n is -1, then we know we have the natural log of that, right? That's very convenient. Now we have to make some stipulations. This is not exactly right. Not exactly. And here's why. Because 1 over x, you can throw a negative number into it. But natural log of x, you can't. So we haven't had this problem before with doing derivatives where the domains don't match. But we do want the domains to match. In other words, if I have 1 over x and I'm talking about -2, -3, whatever, I still might want an antiderivative back there. And that's no good with natural log of x. So we want the domains to match. So if we just say, if we just put absolute values around that x, we're actually fine. Because now the only number that neither of those things accept is 0. And that's fine. If a function doesn't accept a 0, then its antiderivative shouldn't accept a 0. And natural log of 0 is undefined. But if you look at the graph of natural log of absolute value of x, now it covers like both negative numbers and positive numbers. And if you compare that with the graph of 1 over x, you'll see that they have the same domain. It didn't matter going the first way, because if we say, okay, the derivative of natural log is 1 over x, well, then we don't care about negative numbers because they don't belong in the original function. But now negative numbers do belong in 1 over x, so this just makes them also work for the antiderivative. So really, that's the rule. If you did have to memorize these, that's what you would have to memorize. And that does become important when we apply this stuff later. So I'm going to fix that on the table. So go ahead and erase the parentheses, sorry, and put in absolute values. That technically is the antiderivative. There's the two basic trig ones. Antiderivative of cosine is sine. Antiderivative of sine is negative cosine. I'm trying to get you in the habit of putting the plus c. It's kind of like including units. It's just kind of etiquette. If I tell you secant squared, well, you just happen to know a function whose derivative is secant squared. That's tangent. It's interesting, though, we're not going to go through all 6 trig functions, because if you think about it, if I asked you for an antiderivative for tangent, none of the basic trig functions have a derivative of tangent, right? The derivative of secant is secant times tangent. We have seen a function in this class whose derivative is tangent. We saw it one time. I do not expect you to remember it, but we have seen it, and we're going to get it by doing math. So there is a function whose derivative is tangent, but it would not occur to you off the top of your head what it is. So that's not going to appear in this table because we're not there yet. Well, we all like that one, right? What's the antiderivative of e to the x? No, e to the x. Here's your square root rule. The derivative of the square root of x is just the power rule. So just like with differentiation, if I give you something with a radical or a 1 over x squared or something, just convert that to a negative exponent. Same exact deal. Convert it to some kind of exponent and then just use our backwards power rule. So it turns out to be 2/3 x to the 3/2. For a fractional exponent, that's almost its own rule, where it's like the reciprocal times x to the 1 plus n. The antiderivative of a constant is just a constant times x. This one screws people up. So if I give you 5 and I ask you what's the antiderivative of 5, it's actually 5x. It doesn't go away or anything, right? So this is just literally, again, the backwards rule for our constant rule for derivatives. The derivative of 5x is 5. And then the little c is any constant, and the big C is also any other constant, which again is just an ambiguous constant that can be whatever. The derivative of a constant times a function is a constant times the derivative of the function, so that works both ways. In other words, if I ask you for the antiderivative of 3 times cosine, that's just 3 times sine, because when you differentiate, functions come along for the ride. So why wouldn't they do that when you antidifferentiate? So that's one of those things where it's just like, oh, math is simple, you know, it works out the way you want it to work out. Same thing with the sum and difference rule. If I give you a sum of two functions like a polynomial, you just differentiate by going term by term and doing the derivatives of the individual terms. So you do the same exact thing with antiderivatives. That should make sense, right? Notice, why do I only have plus c? Like, shouldn't it be plus c plus d or something? You could, but so c is an arbitrary constant. And if I said plus c plus d, that d would also be an arbitrary constant. So why not just take c plus d, which is already an arbitrary constant, and just call it c? Because you don't know what it is anyways. So there's no difference between having two arbitrary constants added on or one arbitrary constant added on. All that is to say, don't worry about it. Anytime you do an antiderivative, just slap a plus c onto the end and you're fine. So those are the two rules that are fine and work both ways, the constant multiple rule and the term by term rule. If you're thinking about like the product rule or the quotient rule or even the chain rule, there is no such thing as a universal backwards power rule, or backwards product rule. There's no such thing as a backwards quotient rule. There's not really any such thing as a backwards chain rule. We have techniques for reversing those things, but it's not as simple as just like, here are a bunch of rules you have to memorize. It requires some creativity. And again, if you don't take Calc 2, you don't have to worry too much about that. This one throws people off, so I wanted to mention it. If I give you just x, we already have a rule for this. You just have to think about it as x to the 1, right? X is x to the 1, so this is x to a power, right? So the power goes up by 1 to x squared, and then you divide by that same number. So the antiderivative of just x is x squared over 2. So when you see something without a power like that, you have to think about it as having a power. For whatever reason, people just breeze by and they think, oh, it's x, so it just goes to 1. No, it doesn't. That's the differentiation. Now we're going backwards. So convince yourself that the derivative of x squared over 2 is just plain old x. Okay, let's flex our muscles a little bit. Here's an example. You know, I know this looks weird, but it's not hard. This really isn't any harder than differentiation. It's just we have new rules. So we want an antiderivative for little f equals cube root of x plus 3 over x to the 5th plus cosecant squared of x. So we're just going to go term by term. There's nothing new there. But the first thing to do, just like when you differentiate, is to write things as negative exponents and fractional exponents. So you have to be able to do that. Cube root of x is x to the 1/3. 3 over x to the 5th is the same thing as 3x to the negative 5th. And then cosecant squared is just cosecant squared. Now we can use our power rule. And keep in mind that 3 in front of the 3x to the negative 5 is just going to come along with the ride just like it would the other way. So it's just going to be with us in our answer, but it doesn't affect what we do. 1/3 plus 1 is 4/3. You kind of have to do a little fraction math here. So it's x to the 4/3 divided by 4/3. The 3 just comes with. We'll throw it back in at the end. So now remember, negative numbers, whatever it is, it always works the same way. So be careful. The negative 5 goes up to a negative 4. It doesn't go up to a negative 6 because that's down. So we want to go up to a negative 4 if that exponent is negative. So it's x to the negative 4 over negative 4. If you left an answer like this, I don't think I'd mark it wrong, but just, I mean, I think we can all agree that that looks terrible. So, you know, clean it up, I guess. I would like if you cleaned it up. And then the derivative, let's think, the derivative of cotangent is negative cosecant squared. That cosecant squared should have rang a bell. So just like with cosine, the derivative of negative cotangent is negative cosecant squared. So the antiderivative of cosecant squared is negative cotangent. And then don't forget the plus c. So just cleaning it up, dividing by 4/3 is the same thing as multiplying by 3/4. So it's 3/4 x to the 4/3. And then, okay, x to the negative 4th is the same as an x to the 4th being in the denominator. So that can come down to the denominator. And then that 3 is just a constant multiple, so it can sit up in the numerator. So that 3 times x to the negative 4th over negative 4, we can bring the negative out front. So that's the same as minus 3 over 4x to the 4th. And then just simplify that to minus cotangent. So the nice thing about these I mean, your calculator won't do this for you, but you can always check them by just working backwards. Just take the thing you have in front of you and just do the derivative. You know how to do that. It's easy. It's just power rule. So you can always verify it by just saying, okay, the derivative of 3/4 x to the 4/3 is, okay, the 4/3 comes out, that goes away, drops down to 1/3, boom. To do the derivative of 3/4x to the 4th, you would want to rewrite that as 3/4 x to the -4. Use the power rule, 4's cancel out, negatives cancel out. The -4 goes down to a -5, and then the derivative of a negative cotangent is negative cosecant squared, which is plus cosecant squared. So I didn't do that, but I just talked you through it. So with this reverse differentiation, you can always check it by just switching your brain back to derivative mode and just going back the other way, and it's really just simplifying. I wanted to make a note of this. Every function has a derivative, right? We saw that on the exam before this last one. I just made functions that were so complicated, did not have any practical use whatsoever, and you easily told me the derivative. No problem. And that's the case. You can't make up a function that doesn't have a derivative. But not every function has an antiderivative. In fact, if you think about there are an infinite number of functions, you can really say that most don't. And there's some simple ones that don't. For example, there's no function whose derivative is sine of cosine of x. I'm not saying that it's unknown, that this is an unsolved problem of math, like what is the antiderivative for this function. I'm saying it is known that there is no function that has that as a derivative. So hopefully you're all at home going, well, that's not true. What about this? What about this? What about this? Go ahead, try it. See how the chain rule works. It doesn't. You can't do it. So there doesn't exist a function like that. Same with something like e to a power like e to the x squared. That's a very simple function that comes up all the time in statistics, but there is no function whose derivative is that because of the chain rule. Because, okay, if the derivative of e to the x squared is 2x times e to the x squared, right? So how would you cancel out that 2x? You can't divide by 2x because then you'd have to use the quotient rule. Again, just take my word for it. So this isn't like derivatives where I'm just going to throw at you any old function I just made up and say, give me an antiderivative, because a lot of times you just can't do it. So mathematicians have to rely on things like numerical methods and approximation, and a very magical thing called the Taylor series, which you don't get till the end of Calc 2. Okay, so don't worry about that. You should know. So one concrete example, right? You should always be asking, like, why are we doing this, right? What's the point of antiderivative? I told you a derivative is a rate of change, and we saw plenty of applications for that. What the hell is an antiderivative? So I just wanted to throw one concrete example of using this at you. Okay, we're on Mars. The gravitational constant of Mars is known to be negative 3.7 meters per second squared. So that's the thing on Earth that's negative 9.8 meters per second squared. So Mars has less gravity than Earth. We knew that long before we ever went there. It's based on its radius and its mass, which, like, ancient astronomers actually figured that stuff out. Tycho Brahe, those guys. So remember what that is. This is the constant rate at which objects accelerate. So it's not just falling objects. If I throw a rock on Mars, it's always accelerating 3.7 meters per second squared down. If you've had any linear algebra, that's a vector pointing this away. So it's sucking everything down, right? That's why it's negative. So whether or not it's actually falling or being thrown in the air, that's still its gravitational constant. That's why it's called a constant. It's constant. It doesn't change. Okay. So that's A. That's acceleration. That's the object's acceleration. So we want to find the velocity. So I'm standing on top of a cliff and I chuck a rock down off it. Maybe I just drop it. Maybe I throw it. And I want to find the velocity of that thing at time t. So this is the first thing we did in this class. Except now we're doing it backwards and on Mars. So I think that's appropriate. Okay, so A of t is negative 3.7. Forget about the units for now. Negative 3.7 is a constant, right? The antiderivative of a constant is just like cx. We're not using x, we're using t. So the antiderivative of negative 3.7 is negative 3.7 t plus c, right? The derivative of velocity is acceleration. So if we know the acceleration, the antiderivative of acceleration is velocity. So just convince yourself that, yeah, the derivative of negative 3.7 t plus c is just negative 3.7. This is actually a case, so that's it. That's the velocity of anything that you throw in the air after t seconds. This is one of those cases where we actually can use c. It's not just decorative. So v of 0 is the rock's initial velocity. So in other words, if I just drop it, v of 0 is 0. If I chuck it down at 10 meters per second or whatever, that's the initial velocity. So that's what you get when you plug 0 into that function. So let's plug 0 into that function. The velocity at time 0 is negative 3.7 times 0, which is 0 plus c. So the velocity at time 0 is just c. So that means c is a thing. C is that initial velocity. So let's rename it that, right? So you see what I mean? This constant that popped up isn't actually ambiguous or arbitrary anymore. It's a thing, and we just figured out what it is. And there you have it. That's the velocity of a rock thrown off of a cliff or anywhere really on Mars at time t equals 0. So it's negative 3.7 t plus v naught plus the initial velocity meters per second. And physics people, if you're thinking, boy, that sure looks a lot like the equation for velocity here on Earth, well, yeah, it's the same. It's the same gravity. Mars is just has less gravity. So this is all exactly the same. I'm just using Mars because we've already done Earth and we're bored of it. Okay, so there you go. Right from that gravitational constant, we have an equation, a function for velocity. Let's go farther. Find the height at time t. So height is the same as displacement, right? If you're standing on the ground and you're 5 foot whatever and you chuck a rock up in the air, we want to know it has to be straight up in the air, or else we need something called a vector, which we don't have yet. You will in linear algebra and Calc 3. So we can only throw things up and down in Calc 1. Height is displacement. So the derivative of displacement is velocity. So if we know the velocity, what do you know? You anti-differentiate and you get the displacement, right? So now we need the antiderivative for negative 3.7 t plus v naught. And remember, v naught is a constant. V naught is just like c. It's whatever it is, but it is a constant. So when you anti-differentiate it, it doesn't go away. Okay, so here we go. The negative 3.7 comes along for the ride. Remember, t is just like t to the 1, like x to the 1. So the antiderivative of just t is t squared over 2, right? The antiderivative of v naught, which is a constant, is v naught times t, right? Because the derivative of v naught times t is just the constant v naught. So when you anti-differentiate, you get a t in there. So notice something here. When you differentiate something like a polynomial, it gets simpler and it lowers in degree. The exact opposite is happening now. When you anti-differentiate a function, generally it's going to get more complicated. Generally. Well, yeah, pretty much. Okay, so the antiderivative of a constant is just a constant times t, and then plus d. I didn't want to call it plus c because we already had a plus c in here, so why not just use some other letter? So d is just some other constant. It's nothing new. Now we can figure out what d is. First, we clean it up. Negative 3.7 over 2 is negative 1.85. So it's negative 1.85 t squared plus v naught t plus d. The units we'll worry about at the end. Okay, so h naught is the initial height. If you were laying on the ground when you threw the rock, the initial height is 0. If you're 6 feet tall and you throw the rock, the initial height is 6. If you're standing on the top of the cliff, hanging your hand over the cliff, and you throw it up in the air, right? The initial height is however high up off the cliff you are, however high your hand is at that time. Okay, so the initial height could be 0 or it could be anything depending on where you're standing and what you're standing on. So we can plug 0 into that height equation. It's negative 1.85 times 0 plus v naught times 0 plus d. The only thing that doesn't cancel out is d. So you see it? H naught, h of 0, initial height, equals d. So d is a thing. D is the initial height of the rock. So now it's not an ambiguous constant. It's a thing. So instead of writing h of 0, that's what that means, just like with what we call v naught with the subscript, it means the same thing. That means initial height. And there it is. That's the height of a rock thrown on Mars. at time t. Negative 1.85 t squared plus the initial velocity times t plus the initial height. And this is in meters. Again, this is the same exact equation as on Earth. On Earth, it's negative 9.8 t squared. No, I'm sorry, it's negative 4.9 t squared plus v naught times t plus h naught. And so that should make sense. Physics works the same way. Gravity works the same way. It's just a different constant because there's a different constant of gravity on Mars than there is on Earth. So that's pretty good. We figured a lot out there just based on that one number, right? So instead of like turning an equation into a number, the first thing we did in this class was we took Galileo's old negative 4.9 t squared and we turned that into Earth's gravitational constant because we went, okay, displacement, velocity, acceleration. So now we just did that backwards. We knew the acceleration, that's constant. We got that to a linear thing, which is velocity. We got that to like a polynomial, a second degree, a quadratic, that gives you the height. And that's how gravity works, no matter which planet you're on.